Okay, so while we're setting up, I'll just introduce our next speaker. Zsombor Kovacs, he's a guy who really likes to play around with iPads and iPhones. Not always and not mostly Angry Birds, but more about their security issues. And currently he works in England as a penetration tester, so he's one of the guys from Hungary who got his luck, and he's our first Hungarian speaker who's actually from a foreign country. And if you're ready, then the floor is yours.
Thanks for coming. And the short intro, my name is Kovacs Zsombor. I'm a Hungarian dude. I'm a penetration tester by trade, an IT security geek by title, and a hacker by mentality. And as it was said, I work currently for a major financial institution in London. And what we usually do during the day is we break shit and ruin other people's day, and I love this. And this particular financial institution has embraced the idea of iPads. Who here does have an iPad? Just raise your hand. Come on, higher, it's not a shame. Good. But you're the cool guys, you're the lead people. So when Apple introduced iPads back in 2010, early 2010, people usually didn't get the idea first. Like, they didn't know what to do with it. And iPads were developed with individuals in mind. Like, they were designed to be as desirable as possible and as nice as possible. So that people who actually own such a device, they're going to fall in love with their iPads. I think you guys who have iPads, who raised your hands, can testify that. So, but the scenario has greatly changed since then, because as of late 2012, which is, I think now, many corporations and many enterprises got the idea. So they realized that iPads can be used as enterprise devices. They can be used to be given to employees to do stuff like corporate things and sending emails and things like that. And in order to prove this point, I have a fancy table up there. I hope you can read the figures. If you look at the numbers, so we are talking about the order of 10,000 iPads per corporation. And it's a quite recent survey. It's been updated quite recently. And if you look at the numbers, like Korea Telecom, 32,000 iPads. Just imagine, 32,000, that's a lot. And there are some other niche players in this list. Just check out the arrows, like US Air Force Air Mobility Command or the Singapore military. They must be serious. Come on, like I wonder what the military dudes do with their massive camouflaged iPads running around battlefields and checking out Facebook and tweeting and things. So I wonder what they use these things for, but that's just my idea. So now we're talking about a massive amount of corporate iPads. And during this talk, I'm going to use the words iPad and random iOS device quite interchangeably. So when I say iPads, I mean iPods, iPod Touches, iPhones, practically all handheld Apple devices. So they are not niche players. And you want to know what makes an enterprise iPad an enterprise iPad? I'm going to tell you, it's enterprise data. So when it comes to enterprise iPads, enterprise iOS devices, what is the most important thing in those devices? It's not the hardware. It's not the user's emails. It's corporate stuff. If we talk about like financial institutions who use iPads to do sales activity, like salespeople wander around, they distribute iPads to the owing clients, and you can imagine if those presentations with numbers like secrets, confidential information, stuff like this get into the wrong hands, then we're talking about a serious issue. So the question is, when we do iOS-related application testing, is can we extract stuff? Can we extract corporate data? Can we extract confidential information from those iPads? And this, of course, involves we have to think differently than what Apple and the developers expect. On a side note, this is a quite old Apple logo with this rainbow Apple thing. I know, I'm pretty sure you remember this. This is way before the I era. And the funny thing is, the logo, the brand, like the tagline is "Think Different," and this is very funny from my point of view, applied to a company which restricts you as a user from installing anything but what has been pre-approved by that company. So think alike. I think that's funny. Which brings us very nicely to our next topic, jailbreaking. Who here does have a jailbroken iPad? Just raise your hand. For you guys, I have a picture in the right side. For the rest of the guys, there is some text on the left. So jailbreaking means that certain restrictions are removed from the iOS kernel and from the iOS operating system itself. Primarily, it's used to remove the necessity to have applications on your device which has been pre-approved by Apple. So if you have a jailbroken iPad, you can install anything on it practically. And there's this common misconception. So jailbreaking is not the same as installing Cydia. Having Cydia installed is like a side effect of the whole thing. It's much more like a package manager if you think about Linux terms. The process itself works the way it uses exploits to, I think there are a couple of exploits in the DFU mode, DFU ROMs of these iPhones and iPads. DFU stands for, I think, device firmware upgrade or something similar, but I prefer the term device fuck-up mode because this mode is like diagnostical thing. So that's what iTunes uses to update stuff and update the operating system. And this is the easiest way to brick an iPad. What happens is it basically does it adds a kernel patch which removes signature checking. And having done that, you can install SSH, GDB, Cycrape, blah, 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 kind of other things. I highlighted SSH, GDB, and Cycrape because I'm going to use those in the demos. So what? I mean, what's this fuss about? The main thing is that jailbreaking is real. I mean, it's out there. It happens to devices, even if Apple wants to tell you otherwise. And when it comes to designing corporate applications, handling corporate and sensitive data, this is a serious thing to think about. Because according to my understanding, many people who are in managerial positions and they're like system architects, developers, and the like, they simply overlook this option of having a jailbroken device underneath their applications. So when we do penetration testing, we usually use jailbroken iPads, jailbroken iPhones, because they are like the basic toolkit for iOS testing. So performing an iOS test without a jailbroken device is like trying to fix a car without a screwdriver. In order to prove this point, to illustrate what potential an attacker has who has a jailbroken iPad, I have a dummy demo actually, which implements this algorithm. It's pretty straightforward. I don't want to talk about too much. The user enters a password. The application creates a hash of that password and compares this resulting hash with a known good value. And depending on the result of this comparison, we go either to update saying, okay, cool, you're logged in. Otherwise, we do something else. And where this known good value comes from, it's actually irrelevant from our point of view. It can come from the keychain. It can come from some configuration files within the file system. If we talk about like an online authentication thing, it even can come from somewhere else on the internet. So it's, in this particular application, it's the keychain that stores this. It's an MD5 hash of the password. So I'm going to show you guys how this thing works. I hope I have, yes, I have it here. So this is the application. This is the login screen. The password is 1111. It's a very complex one. And here are my uber secret corporate documents here, which I'm going to protect. I log the device again. See like 4444. Try to type to VNC. It's 4444. It doesn't let me in. It pops up the login prompt again. So how can we bypass this? Let's return to our presentation. And the most crucial point of this control flow is this isEqual function, which decides whether or not the entered password is good or something else. So if we can somehow tweak this function, if we can hijack it, we can hack the thing so that it lets us in with any password, so we don't have to know the good one. How can we do this? In this particular example, I don't give you the source code. I hope you can read it. If you can't, the next slide will be much more readable. So just bear with me. So if we look at what's going on the assembly level, this is an actual screenshot from the autopsy provided by IDA Pro on my demo application. So this is the real thing. This is what's going on. And this is pretty much what was on the previous figure. So you can see this. I have a cursor here. So this is the pin code hash function, which obviously performs a hash of the pin code. And the isEqual function is invoked afterwards. And what's interesting is, depending on the result of the comparison, we can go to either we ask the pin code again, or we draw the other screen, which shows the documents themselves. This is, I think, it's much more easily readable. Highlighted, even if you're not familiar with ARM assembly, I hope you guys paid attention to the previous talk because they give you the highlights. They give you the basics. So I highlighted the important bits with red. I hope you can see it. So these are the two function calls. The one called pin code hash isEqual, and this instruction here. This instruction here. This tst.w is a test instruction. It decides whether or not the R0 register, which holds the result of the comparison, is true or false. Like it's a 1 or 0, is a yes or no in Objective-C Boolean syntax. And depending on the result of the comparison, we can either go, we can take the branch. The BNE stands for branch if not equal. So it's like jump 0, jump non-zero in I386 assembly. So how can we bypass this thing? Let's see. We come back to our presentation, to our iPad. Okay, here we go at the pin code screen. And I have a SSH client and SSH server installed on my iPad, so I can see what's going on. So first of all, I have to figure out, I'm going to do this from scratch so that you guys can see what's going on and believe what I say. So first of all, I have to find the process ID. Grab demo, it's 241. Cycrypt, what I'm actually using now, it's imagine it like as a manipulation runtime manipulation framework for Objective-C applications. Imagine it like GDB on steroids. So it gives you Objective-C like syntax. You can manipulate objects in the memory. It's a really good thing. I'm going to use this quite extensively during these demos. So if we come back to the previous screen, I did my homework when mapping the application and checking out what's going on. So I know that when the user presses the OK button on the screen, this detail view controller alert view will dismiss with button index function. I love Objective-C syntax. It's very nice. So this function is what gets called. But the main problem is I want to, if someone of you, those who did like crack me's, know that you kind of get the idea what's going to happen. But the main problem is that iOS applies ASLR. So from a static analysis, you can't tell where this function will reside in the memory, like in which address. That's why we use scrypt. So I'm going to figure that one out. I'm going to have typos. So that's why I use this cheat. So this scrypt thing is, it uses Objective-C reflection so that it can tell you the memory address of each function of each object in the memory, which is a very cool thing. Now in this one, it's this OX8280D thing. So I attach a GDB debugger to this 241. Cool. I set a breakpoint to this address, and so on. So that you guys can see what's going on. So I type, I don't know, 3333, go, and we see that the breakpoint is hit. So it's not a big magic so far. So let's see what's going on. $PC, as you might recall from the previous talk, is the program counter, which is like EIP in i86 assembly. And this is the standard prologue of every ARM assembly function calls. I did my homework, so if we come back to this assembly screen, I'm looking for this particular point in the memory when the actual result of the actual comparison is evaluated. So I did my homework, and I know it's exactly from 62 instructions away from where I stand now. And there we go. This is the one. So if we take a closer look, we see that this is it. So this window is disassembled by GDB, and this other one on the slide came from IDEPRO. So they kind of match. So we set another breakpoint here, remove the first one, so go on, cool with there. We see that this is the test.w instruction, which is the next one to be executed. So we found our point where we're going to change things. So far, we only only what we did. So we inspected the memory and stopped the application, but now we're going to intervene. So what's going on is this R0 register is evaluated. So let's see its contents. It's 0, so it's not equal. So what I need to do is simply set $0 equals 1. Remove my breakpoints. Yes. I come back to my iPad, and I see what's going on, and we load in. So what did we do? We mapped the application with IDEPRO, and what we did is run this application in a very hostile environment in a debugger. We attached the debugger, and we pinpointed the exact point where the comparison result is evaluated. If you recall this figure, this one, this is the point. This is what we tweaked. So we changed 1 byte from 0 to 1, and then the application control flow took the other direction. So this is wow, kind of cool, but jailbreaking should be detected because this can be done very easily with any application. So it's trivial from now to bypass certificate detection, like anchor-based certificate pinning, when the root certificate or the anchor certificate fingerprint is checked, even though it's a valid certificate, the application will refuse connecting to that SSL endpoint. So applications should prepare for jailbroken devices, but how can they do this? I gathered a couple of methods. The first one is the most widespread. I mean, it's out there pretty much everywhere. What it does is checking for known residual artifacts of the jailbreaking process. So we're looking for stuff like /war/log/cd.log /war/ssh/bin/su and stuff like this. And in case one of these files exists, it's an evidence that the device is jailbroken, and the application can act accordingly. This is the most widespread and most easy to implement and the most compatible, because this works in simply all iOS versions. Back in the day, in iOS 3 API, Apple used to have a function which told the application in a programmatic manner whether or not the device is jailbroken or not, but that was too easy to hijack. So they simply ditched that function call. So at this point, each and every application has to implement some kind of jailbreak detection on its own. Another option is to do a fork syscall on a non-jailbroken, like an intact kernel. If you call a fork function call, then the iOS returns a 0, so the seedbed, the sandbox doesn't allow you to do forks on your application. That's also widely used because it's very easy to implement. Another option is to check the size of the file system tab, because in iOS, in intact iOS versions, the size is well known and static. In the jailbroken iPads, it's going to be different. Then you can check for the number of dynamic libraries which are loaded in the memory, and the permissions which they are loaded with. This is much more getting like voodoo, because with newer iOS versions, these parameters change. So if you want to use one of these methods, you're going to have to prepare your application for newer and newer iOS versions, which is a very nice and very popular thing in amongst iOS developers. And I left the final one when the application tries to build a TCP connection to localhost 22, which is the SSH port. This is a very stupid thing to do. It's very, very easy to bypass, but it's there anyway. So I've seen it. The main problem is that when an application tries to decide whether or not it runs on a jailbroken device, it's pretty much like when you try to decide whether or not you're in the matrix, because the matrix controls everything you see, you touch, you feel. So you can't decide. And you only can do your best to decide whether or not you're running on a jailbroken device. But again, this doesn't work in any cases. There's no silver bullet. So this is like a theoretical problem which cannot be solved. In order to prove this point, I made a very simple kind of dummy jailbreak detection routine, which all it does, even if you're not familiar with iOS and the Objective-C syntax, it's pretty straightforward and easy to see what it does. So the keys, there are two functions called dirty device and clean device, which in this example, they just simply pop up an alert window. And depending on the existence of the /applications/cdo.app, the application control flow takes one branch or the other. So it's not a very big thing. I show you guys a couple of things how to bypass this. It's out there. I've seen it in many, many applications. At this point, I'm talking about like manual bypass. I don't want to use applications which are available from the CD or repo, and they tell you that they implement a algorithm which hooks into iOS system calls and does this thing kind of automatically for you. I'm talking about doing everything manually. The first thing is like the ECDC of jailbreak detection bypass methods. It simply take a hex editor, fire it up, open the application binary, and overwrite the strings which are looked for. It's dirty, it's very, very ugly, but it works. It's much more interesting if we do this in a more intelligent manner, because this previous method with the hex editing thing, it's obviously going to screw the application integrity. So if in case the app implements some kind of integrity check, then it's going to fail. So we're going to use a much more intelligent approach. We use GDB. The key point here is to check the existence of the CD.app application or file. And this file exists at path, which is highlighted in red. That's the API call in iOS, which does the check. There are a couple of other options where to put our breakpoints. Probably we can use this function call, this condition check, similar to the previous example with the test.w. That's what we're going to do in the demo. Or alternatively, we can hijack the dirty device function, which gets called when the device is jailbroken. So when talking about realistic, like real-life applications, such dirty device functions can implement like wipe. They can remove themselves. They can't remove themselves, but they can delete everything which the user entered. Like if they contain some kind of confidential data, they can probably wipe those. But that all depends on the application itself. So we're going to pinpoint our breakpoint to this is jailbroken function. I made a small figure here, which shows the calling stack. So when we get to the point where the file exists, the path function is called, that this is the control flow. It's going from down to upwards. So before the file exists, the path function is called. Is the jailbroken function, which is in the calling stack. And before that is the jailbreak detection. So that's nothing really, really fancy here. But this will all make sense in a minute. I'm going to quit this one. Yes. Come back to my iPad. This demo application is simply, this is an excerpt from the actual source of this app. So it checks whether or not the cd.app file exists or not. In case it exists, it pops up a jailbroken function. Otherwise it's going to show a clean device. So let's get back here. Fire up GDB. Okay. We set up a breakpoint at the file exists at path function. I think I bring it back to you so that you can see what's going on. Probably like this. So let's start it. And we already hit the breakpoint. Let's see which parameter was it called with. So if you recall the previous talk, in ARM assembly convention, the calling convention, it's the R0, R1, R2, R3, which hold the parameters for the function calls. And in this particular example, the file exists a path function. The R2 contains the string that contains the file name. Because when we do it in a more sophisticated and bigger app, this function gets called many times, and not only with our jailbreak detection routine, but with everything else. So we see that, yeah, this is the real one. We have to find this. So let's see what's in the backtrace. GDB doesn't tell us which functions we have here, but if we look at what's in the calling stack down here and in here, we see that these are the same. So I'm going to hijack this one, set another breakpoint. We hit the breakpoint, and let's see what's in there. We suspect something. So if you recall the previous example, this TST, the W function, or the instruction, is what decides whether or not a condition is true or not. So in this case, is the result of the is jailbroken function, which the result of which is held in there. So theoretically, we should have a we have a 1, so it's a logical, it's a Boolean true, so the device is jailbroken. All we need to do is to set R0 to false. Remove my breakpoints, come back here, and it says it's a clean device. So it's that easy to bypass. And this was actually a kind of laborer's thing to do, but I'm going to show you in a couple of minutes another bypass method, which is much, much more easier to do. So coming back to our slides, this method, the key of this jailbreak detection thing is this is jailbroken function. So how cool it would be if we could simply replace that function with something else, our own devising. So can it be done? Yes. And the answer here is method swizzling. That's a term used for runtime manipulation of the framework and the application memory. The basics are that Objective-C is a heavily reflective framework. So when you do object function calls in an Objective-C program or an Objective-C application, the way the whole framework processes this function call relies heavily on the names of the functions. And in the memory of every iOS application, there is an array which holds the actual memory addresses for every application and every object which are in the application, and each and every function which belong to those objects. So how cool it would be if we could simply replace this. We could manipulate the contents of this table. And this is exactly what we're going to do now. I'm going to quit this. Yes. Clear. Come back. Follow JBT. Okay. We use secrypt again. No. JBT. Now, what we need to do is to come back to the code, and I didn't include the actual object names in there. But it's not very important because what I'm going to enter is this line. And what did I just now? I created a new function within the application memory, which all what it does, it returns a Boolean false value, and that's all. And in the first half of this line, I simply overwrote the isJailbroken function within the memory, which is kind of cool, because now if I come back to my application and fire it up again, it should say it's a clean device. And I didn't have to do anything with GDB. I didn't have to do any disassembly. I didn't have to set breakpoints for that matter. I didn't have to literally do anything that can be considered laborious or work intensive. So what's the point here? When we talk about an iOS application which implements any kind of protection routine, I spoke about certificate checking. I spoke about jailbreak detection. I spoke about responding to remote wipe commands, which comes through the Apple push notification service. They are all implemented with such function calls, which can be very easily hijacked on a jailbroken application, jailbroken device. So what are the conclusions? First, do not rely on jailbreak detection because of these demos I showed you. Don't rely on the assumption that an attacker is unable to deobfuscate the binary or to reverse the application. I showed you some excerpts from IDA Pro and GDB. So it's very easy to disassemble an iOS binary. It's very easily readable. I think it's much easier than if you think about C++ on IE386. If we talk about a jailbroken device, practically anything on the device is to be considered tainted. Anything is considered untrustworthy. So don't rely on the keychain. Don't rely on security checks. Don't rely on the PIN code. Don't rely on anything. The only solution here is to assume that the environment, the actual device and the iOS environment is hostile. So what we need to do is to implement crypto and use it in a proper fashion. This is one of the usual solutions we usually suggest. So I give you a little time to comprehend it. So the way an application should do, say, encryption routines, is to create a complex password, enforce that complex password. When the user enters that password, is boost up an AES key from that password and start decrypting data. Don't have any data that is stored and check whether or not something is equal to that data. Just start decryption and check whether or not the resulting value of the resulting data is sane or not, whether it makes sense or not. If it makes sense, the user did it right. He knew the correct password. Otherwise, the user simply forgot the password or entered it incorrectly. And the whole point of this looks fairly complicated to the original example, to the login bypass I showed you earlier. But it makes sense because on a jailbroken device, there are no secrets. An attacker has access to everything, and not even the application itself is to be trusted. And all you can do is to use crypto properly and to use other methods to raise the bar as high as possible, so that to make the job of an attacker as hard as possible. So that's pretty much what you can do. And this is my takeaway message. So don't consider any iOS device trusted when dealing with sensitive corporate data. Thank you very much. And I have a couple of references and links up there if you're interested. And I think we have time for a couple of questions. Do we have? Okay, a couple of questions. Sorry, I can't see anything. Sorry, speak up. Speak up. The question was that. Sorry. Yep. The question was that can we consider a jailbroken device worse in any manner than a non-jailbroken device? So the question is, I think they're equal. They're just used for different purposes. And the fact that you mentioned that any device can be jailbroken, pretty much. But now it's not entirely true. If an attacker physically steals an iPad, he has the opportunity to jailbreak it and then do the dirty magic we showed you. So even if the employee did not jailbreak his device himself, the attacker can very easily do that. That's true. That used to be true. But now with iOS 5.1.1 and iOS 6, if you have a screen lock, a pin lock implemented, it's set on the device, you can't jailbreak it because you can't access anything. You can't reboot it to DFU mode because it requires to unlock the screen first. And if you try to jailbreak with Red Snow or Purple Rain, iOS 5 or up, iOS 5.1 or up, it tells you, I'm sorry, dude, I can't do anything with a pin protected device. Another question? 3, 2, 1. Cool. Thank you very much.